tool that I've been building for the past few years called thinkCausal. And it's a tool to help researchers learn while they do. I've been wanting to make this kind of a tool for a very long time and finally got some funding to do it and some great people, and we're having a lot of fun. So I'm Jennifer Hill, I'm from NYU University, and I guess you know who you are. So this is joint work with a number of talented folks, students, and colleagues and researchers that I've been working with from afar who are not-for-profits. I particularly want to call out the contributions of George Perrett, who basically took my crazy ideas and turned them into reality with his excellent, shiny programming skills. And also Zhenhui Yang and Joe Marlowe were super instrumental in this, but it's really been a team effort. That said, you know, anything that you find worrisome or problematic is, you know, attribute to me, and all the good you see attribute to the rest of the team. I also need to thank my funders. IES has been a tremendous sponsor over the years, and part of this was also funded by the Office of Naval Research. So the first question is, why should you care about causal inference? Well, if you just read the newspaper from day to day and look at the headlines, you probably will end up seeing quite a few that are causal in nature. They're posing causal questions, and often the articles are purporting to answer the causal questions, whether they can or not in reality. People care a lot about causal inference because it affects practice, policy, all kinds of aspects of our lives. So I like to say that all important research questions are causal questions. It's a little bit of an oversell, but not too far from the truth, I don't think. So what happens if we get causal questions wrong? Well, we risk losing money, time, potential, and lives, right? If we didn't understand the impact of the COVID vaccine, a lot more people would have died, right? And so there's a reason why drugs only get approved in the US and many other countries through randomized trials. It's because we have to get the causality right. We have to actually know if this thing causes that thing, you know, and by how much. So it's really important if we ever want to make decisions about how to proceed with lives. Okay, so that's great. The problem, of course, is that causal inference is hard. It requires either strong design or basically a lot of assumptions plus a little bit of scaffolding from some tools. So we spend a lot of time as statisticians building the tools, but in the causal world, those often go hand in hand with a lot of assumptions. So we want to make sure that when researchers are using the tools, they understand the weight of the assumptions they're making. So I'll walk through some causal inference basics. This may be old news to some of you. It may be new. Hopefully it's not too much of a repeat of things you already know. So causal inference is about making fair comparisons. If we have two groups of individuals and one group got a treatment and the other didn't, what we're hoping is that the only thing that is different between those two groups is that one got the treatment and the other one didn't, so that it's a level playing field and we can attribute any differences in outcomes to that treatment. Unfortunately, with observational data, which is what we most often have access to, we typically don't get that level playing field. We get a group of people who got the treatment who may look very different than those who didn't get the treatment. More insidiously is the situation where they look very similar, but in fact, they're quite different in terms of things that we can observe: their resources, their mood, their motivation, their grit, how much time they have, right? All kinds of things that could be different that may be very difficult to capture in whatever we've measured about them. Okay, so fair comparisons gets formalized in the statistics world, usually by talking about counterfactuals. So those are the building blocks of causal inference. And to understand causal inference, we need to understand counterfactuals. Well, this is a pretty basic idea in philosophy, but to motivate it, we'll have a very simple example. Consider the following scenario. Joe is struggling in math. Joe uses an online tool for extra help with the material. Joe scores poorly on the subsequent math test. The question is, did the online tool cause the low test score? Right? When you're in that situation as a human, you always want to attribute, right? You're always making inference without knowing the counterfactual. But in reality, we have no idea whether the online tool caused the low test score. It might be the test score would have been lower were it not for the online tool. We don't know unless we know what would have happened if Joe had not used the tool. We need both of those pieces of information, right? So causal inference always assumes this comparison of counterfactual states. So the effect of the online tool for Joe is a comparison between Joe's test score after classroom instruction plus the tool versus Joe's test score after classroom instruction alone. Okay, so we'll label those as Y1 and Y0. Those are potential outcomes, and they are the statistical notation we use to formalize the idea of the counterfactual. That lets us, in theory, if we could see both of those, we would know the causal effect for Joe. We could calculate an average treatment effect across everyone in our sample, or perhaps for a population, and we could get various subgroup effects. Sorry. But again, the problem is we can't see both potential outcomes at the same time. So in essence, we have a missing data problem. If Joe uses the tool, the missing data is what would have happened without the tool. If Joe doesn't use the tool, the missing data is what would have happened if Joe had used the tool. In either case, we're missing a vital piece of information. So this brings us to our assumptions. So in the absence of a randomized experiment, we typically consider two types of assumptions, structural and parametric. The structural assumptions have to do with the relationships between our key constructs, our potential outcomes, and our treatment for the most part. So a key assumption that we typically make to move forward is ignorability. The general form of this assumption is this. Can you see my cursor when I do that? Okay, is this one. It says we need to assume that potential outcomes are independent of the treatment, conditional on all the covariates, all the pretreatment variables that we can measure. So in essence, that's like saying, if we had two groups of people who all had exactly the same values of all their covariates, it's like we flipped a coin, whether or not they ended up in the treatment group or not. Okay. It's a pretty big assumption. There's a simpler version that usually only holds when we have a randomized experiment. This assumption, just to make things even more confusing, is called different things in different disciplines. So you might see it referred to as no hidden bias, selection on observables, all confounders measured, exchangeability, exogeneity, and there are several others. Okay. So the design solution is what we always want as statisticians. Let's design away the problems. I don't want to fix it with a fancy model. I'd much rather have a design that solves my problems. And that's great when you can get it. So a randomized experiment creates fair comparisons just through the flip of a coin and allows us to satisfy this more constrained version of the ignorability assumption. A randomized block experiment does the same thing, where as long as I randomize within blocks defined by X, I still get to satisfy ignorability. So that's terrific. So within each block, it's, like I have a randomized experiment. With observational studies, instead, what we end up doing is assuming ignorability conditional on our covariates. And in essence, we're hoping our study is like a complicated randomized block experiment, a really, really complicated one, where if you looked in like this multi-way array and found your neighborhood in that covariate space, again, we're hoping that in that neighborhood, it's a flip of a coin. whether you end up in the treatment or control group, okay? So this assumption is the same. It's just that in the randomized block experiment, it's satisfied by design. In an observational study, we have to make a leap of faith. So this is our leap of faith solution to the problem. So that's the hard part. Of course, statisticians have spent 30 years working on the easy part of the problem, which is how do you do this conditioning? So that's what I'm going to talk to you about today. Okay. So again, the randomized experiments are great, but they're rare. They may be limited to narrow questions or populations. And even when we can do them, it may still be challenging to understand when, why, and for whom they work. Observational studies are often necessary due to ethics, logistics, time, money. And the key usually is to adjust for many covariates. Another way of thinking about that is that the covariates are acting as our proxies for the potential outcomes. And that's our way of satisfying ignorability. So the more covariates we have, the stronger the parametric assumptions. So there's a tension here. I want to control for a lot, so I believe my ignorability assumption, but the more I control for, the harder it is to do that in a way that I believe my model. This slide basically says that same thing. Okay. So how do I appropriately condition on many pretreatment variables? So that's where we get to parametric assumptions. And the parametric assumptions, again, are the easier ones to solve because we've been thinking about how statisticians have been thinking about how to model data for a very long time. And the data have the ability to tell us when we're doing the wrong thing to a certain extent, right? It's a little harder in this world because we don't have the potential outcomes, but still, at least we can see whether we're doing the right thing by our observed data. Yes, and I love this cartoon. Okay, so this is where our tools come in. So just to do a little beating up on regression. Regression is one way to adjust for lots of variables, right? Here's a situation where we're just trying to adjust for one variable. Pretend we only have one confounding covariate and it's a pretest score. So I am showing here a plot that looks like nobody's data because the points are so close to the true lines. The true response surface, in other words, the relationship between each potential outcome and our one confounder pretest, those curves are shown by the solid lines. And the red ones refer to the treatment group and the response surface for Y1, and the blue refers to the response surface for Y0 and the control observations. And you can see that if we just fit a linear regression to these data, it's not doing a very good job. And I always think of this as a cautionary tale for how you teach linear regression, because linear regression, this is like one of the simplest linear regression models you can imagine, right? There's one binary variable, one continuous variable. And although we always teach our students not to make predictions beyond the scope of the data, this model is implicitly doing that, right? It's saying I know something here when I don't know anything about the treated response surface here because I've got no data points, and up here as well. So I'm really extrapolating beyond the range of my data when I'm fitting this model. And accordingly, it's doing a bad job, right? It's not fitting the data well, and I'm going to get a pretty bad estimate of the treatment effect if I use this, right? Because what is the true treatment effect here? Well, if you just look at the treatment effect for the person with pretest 40, it's the difference between the vertical distance between these two lines, right? If I did that for all of the treated observations, those would average up to the effect of the treatment on the treated. If I did it for the blue observations, that would average up to the effect of the treatment on the controls. And if I did it for all of them, that would be a representation of the average treatment effect for everyone in my sample. But again, the linear function is not doing well because it's the wrong fit, right? It's the wrong model. Now, if we had literally one pretest and we were trying to diagnose this, we would see the problem, I would hope. Hopefully we would do some regression diagnostics, we'd plot our data and we'd see. Once you have 30, 50, 100 covariates, it's going to be really hard to diagnose when you're doing a bad job with regression. Okay, so I hate to beat up on regression, but if you are going to beat up on regression and say correlation is not causation, the real problem here is this, not that some of the other methods that change the modeling assumptions are solving the big problem that they all have, which is that ignorability is probably not satisfied. Okay, but we'll beat up on regression. So how does machine learning come into play here? I'm going to give an example with an algorithm that I like to use, that I've been touting the benefits of for now almost 20 years, called Bayesian additive regression trees. This was developed by Chipman, George, and McCullough. All of us had a hard time getting our papers published. I think they had this algorithm, starting in like near 2000, and I had my first BART and causal inference paper ready at like 2004, but it took all of us a long time to get published. So anyway, how does it help? Here is a simple regression tree fit to this response surface. So here's the regression tree, and the fit I'm just showing as the step function in blue over here, right? So, a simple tree just bifurcates the data into subgroups, such that those subgroups minimize the variance of the outcome. And then the fit is just the mean in each subgroup. So that does a decent job. You could make this, a more and more complicated tree, but the problem with a single tree is that it's really hard to not overfit the data. And so that property of regression trees motivated development of boosted regression trees, which are sum of trees models. So this is distinct from a random forest, which is a model averaging. This is sum of weak learning trees. So how do we think about this? Well, imagine fitting one small tree to a response surface like this, right? And that's going to soak up a bit of the data. Now here I've got multiple variables as opposed to just the one. But it's going to explain a part of the variance of the data, but not all of it. If I subtract that out from the outcome and get the residuals, I could then fit another tree to those residuals. Take that out, subtract that out, get new residuals. That's everything that's still not explained. Fit another tree to that. And that's a backfitting algorithm that's used for typical boosted regression trees. And you might fit 200 of these in a sum. The problem is that it's easy to overfit then. So usually the fit from each of those is multiplied by some small constant that is chosen by cross-validation. And so that's like the shrinkage term that's used. So what Chipman, George, and McCullough did was to embed this model in a Bayesian framework. Super clever idea. And they instead use prior specifications to avoid the overfitting. And so, and you can cross-validate if you want to, and sometimes that helps, but most of the times just their default prior specification, which I won't go into today, but it's very clever, does a great job at avoiding the overfitting. So to show with our example, here is a BART fit to the same response surface. It's shown with the dashed lines. So it's really doing a very nice job. Another representation, I'll get to another representation in a second. So how are we doing this? Basically, we're fitting the BART model just to our regular old data, which has some covariates, and it's got a treatment variable, and it's got an outcome. And then I'm making predictions in two data sets that look a lot like that original data set. In one of those data sets, I've set all the treatment variables to 0, and the other one I've set them to 1. So I can get, for each person, a posterior predictive distribution of their potential outcome in each setting. So for person 1, this would be the posterior predictive distribution for the Y0. This is the posterior predictive distribution for their Y1. I just take the difference of those two distributions to get a distribution for their treatment effect, their individual level treatment effect. Now, we probably don't want to use those individual level treatment effects outright, but we can average them up to get any kind of quantity that we want. Here I'm showing with the same data For each treated individual, 95% posterior intervals for the Y1s for each of these people, and the Y0s. And so you see what happens, that for this person, I know a lot about their Y1, and for their Y0 interval, which is down here, I know a fair amount actually as well. And it's only when we get out here and we don't have so much data that we end up getting pretty wide intervals. But what's happening is BART is at least telling us, hey, I'm uncertain there. You should be really careful there, which is good to know.
Jennifer, I got a question. Are those intervals for the accuracy of the curve that you're fit, or the accuracy of the points, prediction interval for somebody at that point?
Exactly. It's basically for someone who has that covariate value at that point, so someone with a pretest of 50 would have an interval like this.
Thanks.
So here are the intervals for the treatment effects. Here's the true treatment effect. If you compare that to what regression is saying, I mean, granted, it was a very unsophisticated regression model we fit before, but regression had one estimate and was very confident about it. So that's very misleading. So there's been a bunch of scholarly articles. This is just a snapshot of them, expanding BART for other kinds of causal inference settings, et cetera, and some competitions that it's been in. So some of the nice features: it helps detect and remedy violations of common support. It can explore sensitivity to violations of ignorability. It identifies treatment effect heterogeneity. It performs well when generalizing to other populations. It produces coherent uncertainty quantification, and recently has been extended to include multi-level models. So I'm looking at the time, I'm just going to do a couple of quick demonstrations of what those bells and whistles look like. So back to the overlap setting, this response surface is basically the same one as before, but I don't know if you remember, there used to be a little point out here. So now I've gotten rid of it, and BART is struggling, right? As it should be. We can't do inference in parts of the covariate space where we don't have the data, and we shouldn't be doing it, right? We don't have any business doing it. So the nice feature here, though, is that BART understands when it starts to not have enough information, and the uncertainty intervals get wider and wider. So along with Yusung Su, I developed some strategies to help identify when you're in this situation that have to do with how large these intervals are relative to these intervals, and gives you a strategy for identifying which of these observations you just should not be making inferences about.
Should there be a similar problem on the left side of that graph with the red?
Yeah,
data?
so sorry, I was thinking, so I'm focusing on the effect of the treatment on the treated, but yes, if you were focusing on the overall effect on everyone, you would have the exact same problem over here. But I only fit this for the treated observations for this example, just to kind of narrow the focus. Thank you for pointing that out. Sensitivity analysis, really, I need, a long talk to describe what's going on here. So it's a little unfair to put this up, but the basic idea here is to try to understand how wrong you could be if there's an important omitted confounder that you have not included. So this strategy creates a model both for the treatment conditional on the covariates and the outcome conditional on the treatment and covariates. And both of them are also conditional on an unobserved covariate, U. And so we toy around with, well, if the coefficient on U was this big and the coefficient on U in the other model was this big, what would my bias look like? So these response curves say, this is the naive treatment effect estimate if I assume there's no confounding, and these show how that treatment effect estimate would change depending on different types of confounding that are characterized by these sensitivity parameters, reflecting, again, the relationship between that unobserved confounder and my treatment and outcome. There's a bunch that's been written on treatment effect heterogeneity and generalizability. Here are some papers. basically those two are intricately linked. If you can get a good idea, if you can characterize well how treatment effects vary by different kinds of people, then it's easier to generalize to other kinds of populations that may have a different makeup sociodemographically or however. So that's, there's been a bunch of papers written about that. Detection of treatment effect moderation. I'm just going to give a quick example from a data challenge that was associated with the 2017 Atlantic Causal Inference Conference, where the people running the challenge created a data set which had hidden structure that we couldn't see, but it was based on a large, massive randomized experiment. And our goal was to estimate the average treatment effect and try to detect effect modification by covariates. So in doing this, at one point I was in a little team of 3. We made this plot of treatment effects at the school level. It was multi-level data, treatment effects at the school level, and which is hard to do if you don't have an algorithm like BART. You know, it's hard to do with propensity scores or anything like that, because you just don't get this fine level of detail. And when I made these plots, I was trying to understand whether these two covariates on the x-axis were moderating the treatment effect. And I saw these weird kind of this whole subgroup of points that didn't look like the others. So I threw those treatment effects into a regression tree and found out that, oh, that was almost entirely predicted by this variable called urbanicity, like how urban those schools were. And once I identified that, it revealed this moderation effect that, I mean, of the 9 teams competing, the only 2 that identified this moderation were the 2 machine learning based teams. It was really hard to see otherwise. Okay, and we've recently extended BART to partner with STAN, so that we have now an extension of BART that has a parametric piece and a non-parametric piece. The primary motivation was to have a more principled multi-level model structure to accommodate group data structures, et cetera, to make that parametric. So that piece has worked well, but in theory, it could be used for much more general forms of models as well. And we've got many other features to come. We've got models for binary outcomes, but we don't love them. We're trying to make them better. Other kinds of outcomes, count, survival, et cetera. All kinds of other things coming in the future. Okay, but that's not why I came here to talk to you. It is kind of. So many of these features are captured in a R package called BART Cause. You can go onto CRAN, it's sitting right there. It's pretty easy to use, I think, for if you're an R user. So why shouldn't this be good enough? Why doesn't everybody use BART Cause?
Jennifer, are you going to say more about STAN, or was that kind of just an aside that we
I was an aside. I'm happy to take questions. I'd rather take questions on that at the end, if that's okay.
Sure enough.
To the software, but yes, happy to talk to anyone about that. Okay, so there are lots of barriers. I work with a lot of applied researchers. None of them use R. Right? So, I really want to, I think as statisticians, we should be moving to much more of a teach a man to fish model, as opposed to we have to do everything for everyone. It's not viable for all the data that are out there and all the questions that need to be answered. So not everyone uses R. People don't like to use tools they don't understand. And arguably, we probably shouldn't be encouraging people to use tools that they don't understand. So that's why we built thinkCausal. So thinkCausal is a user-friendly way to access sophisticated causal inference tools, and it's got educational components for just-in-time learning. So I'm now going to switch over. Can you see, now you should be seeing the tool. Is that what you're seeing? Okay.
Yes. Yep.
Great. So this is what it looks like. And immediately when you enter, you can either start learning about causal inference, or you can start analyzing your own data. Oh, I forgot, there's a little setup. Getting my talk. All right, so we're going to pretend that I'm a researcher at the Department of, or data analyst at the Department of Ed in Big City. I have a BA in economics and a master's in public policy. My preferred software package is Stata. I've never had formal training in causal inference. I have lots and lots and lots of data on children throughout the city. And I'm frequently asked by my superiors to make policy recommendations based on the data. Pretty much they're asking for answers to causal questions at that point. And the research question that I am focused on today, I need to get a report out in 2 hours to my bosses. Does early intervention lead to higher test scores for at-risk children? Okay, so I jump in here, forget about the learning. I just want to analyze my data. I jump into here. This is all built into R Shiny, by the way. I can upload many, many different kinds of data sets. That was really easy. Move along. I'm going to choose my outcome. I'm going to choose my treatment. I know I don't have a randomized experiment, so I guess I've got an observational design. There's some information here about which of these variables I can include as covariates. I'm going to include them all, but note that I would be alerted if I try to include an ID variable, and we're warning people not to include post-treatment variables, et cetera, with little hover-overs to explain to you what that means. I move on. Nothing I hate more than inheriting a data set that has stupid variable names that I don't understand. So I get to just change these at will. These classifications are really just for the plotting functions. I'm telling you that as developer, not as pretend researcher. So they don't have to be quite perfect. And I'm going to save and continue. And I've got this beautiful interface just to make whatever plot I want. So I know that I care a lot actually in these data about the relationship between birth weight and the outcome. It's already filling by color. I'm going to do that by shape too, because it's, size is what I wanted to do. That makes it more clear. So what I'm seeing here is that is something that maybe I would have forgotten if I hadn't seen this visualization, that there's not a lot of overlap in birth weight. And now I'm reminded as researcher, oh yeah, that's because this program was targeted at low birth weight children. So of course, I'm not going to see anyone over here. And that informs the kind of causal inference I want to do. If I want to download the plot, I can. Lots of different plots you can make. I'm not going to obviously go through them all, but I'm going to spend a tiny bit of time on this overlap plot because I really want to investigate this a little more. I'm going to go back to birth weight. And where's birth weight? Here it is. So it's showing me the distribution of birth weight in the treatment group and in the control group. Now, this is going to change depending on the estimand. And now that I kind of boldly jumped into analyze, but this may be a point when I say, actually, I don't really know what an estimand is, and I don't really understand those things. So maybe just for a second, I'll jump out to the learning modules. So here's a learning module on causal estimands. It's embedded in a story about marathon runners and special shoes that they use to run faster. We have visualization that talks about the data we might observe for those two different groups and how that differs from what their actual counterfactuals are. Nice little scrolly tell. The individual causal effects it walks through. And then in my favorite visualization, it'll show you the individual level causal effect for each person as a comparison between their factual and counterfactual outcomes. And it'll throw those individual level treatment effects down on this plot and show you how that leads to the estimate of, the true average treatment effect. So you get to see a relationship between those. It moves on. If you don't understand what potential outcomes are, you could jump over to potential outcomes and have a little thing about where you learn about potential outcomes through monsters. Who doesn't want to learn through monsters? Anyway, and at the end of this, after it walks you through all of this, it'll give you a little quiz to make sure that you're understanding what you're doing. Okay, so now I understand that. Popping back to analyze, going back to overlap.
Can we make that quiz required for people who are going to publish things analyzed here?
Yeah, let's team up with some journals. I love that idea. I love that idea. Okay, so I see if I just limit to the trying to make inference about the treatment group, my overlap is just fine. Because I have enough controls to kind of act as empirical counterfactuals for my treatment group. Okay, fitting the model. I don't have to run 13 lines of code. I just push a button and I get this cute little visual, and it will display it as a posterior distribution. It's taking a little longer than usual. Not sure why. There it is. I don't want these bells and whistles right now. So it's giving me a posterior distribution, but also an estimate, standard deviation. I can plot the mean or the median. It's giving me a confidence interval, and it's even giving me a causal interpretation. If I'm worried about the causal interpretation, I can switch to a non-causal interpretation too. That's fine. Now, if I wanted, I could have broken that down by subgroups. I didn't pre-specify, but I could have pre-specified subgroups. This also shows me what all the individual, this is called a waterfall plot that shows me all the individual level treatment effects. They're just sorted by order of magnitude. If I want to see what predicts the variation in the treatment effects, it'll throw it into a regression tree for me, and I can adjust how deep I want that tree to go. And it'll tell you, in theory, and later, it'll tell you what that plot. Some of these aren't totally active right now, but they will be one day. And I can do some exploratory subgroup analyses. So I could break this down, for instance, by birth weight group, and it would give me a separate posterior distribution by birth weight group. And if I want, I can just overlay that and it'll overlay them. One of my favorite parts that's currently slightly broken, but should be fixed soon, is that I can download a log of what I did and an R script. So this should be fully reproducible. So if you need to submit the script of what you did to your journal, or if you're leaving your job and your coworker needs to know what you did. I mean, I probably don't have to sell this room on reproducibility. Really nice to be able to download your script and be able to recreate exactly what you did. Okay, so I'm going to come back here so I can wind up. So the idea is to make it easy, but not make it so easy that people can make lots of bad choices. We're toying with versions of this where we are more or less paternalistic. Our next grant proposal will be around user testing with a wide variety of researchers in the field to get a sense of what happens. We've done a lot of user testing with students. I taught about 80 causal inference students in the fall, and I've got about 80 right now. So luckily they need extra credit and they're really happy to come and user test. And we're going to put them in a randomized experiment this spring and see how it works as a learning tool. So we're having a lot of fun. But, there's a lot, the devil is in the detail in terms of how this gets used in practice. And we really want to make sure that we're scaffolding people to make the best choices that they can. So our goal is, though, to help you minimize your assumptions, understand your assumptions, and follow reproducible data analysis practices. Here is a link to it. It's freely available. Anyone who wants to use it for teaching or for their own research or whatever, we would love it. We would love feedback. So what's next? Basically, we need you. We need people to spread the word. So again, you can try it whenever you want. You could give us feedback. You can help spread the word about it, particularly if you like it. And you can join the cause. So if you are interested in making tools, either working on the kind of analytical side, you want to do BART research with us, or because we've got part of our team is working on extending BART for various in various ways, and part of our team works more on the educational components, and part of our team works more on the user friendliness of it all. So we are happy to have more people join the cause. So thank you for your time.
Thank you for your time. That was wonderful. I obviously got a chance to ask a lot of my questions. I haven't seen others other than Charlie was asking about Stan earlier. I don't know if this is an appropriate time or,
Yeah.
well,
Sure.
but now a question showed up. Can current model or BART accounts for multi-level data structure, such as randomized cluster design or grouped data?
Yep. So that is not in thinkCausal right now, but it is in a package called Stand for BART, which is available on CRAN. And we just published a paper in Entropy on it. So if you email me, I can, send you that link or whatever.
Stand for BART sounds not like R, but something else. So is it available in R as well, or no?
Stand for BART is R. Yeah.
Is R, okay.
Yeah. So it's basically it's a marriage between the two algorithms. We for a long time wanted to incorporate BART in Stand, but that's for a lot of structural reasons not really possible. So instead, it's all built kind of in R and C++, and the algorithm just jumps back and forth between the two sides of the model.
So what you said there are several R packages behind this. thinkCausal is the shiny app, but what are the R packages?
So the BART cause is the main one, but the other ones are treat sense, which may not be currently active. So the sensitivity analysis plots were in a package called treat sense. At some point, we have to just pull that into BART cause because the person who was the kind of primary driver of that left academia and doesn't really care about keeping the package updated, which is understandable. And it's hard to get funders to fund software. Anyway, so IES is really good about that, but other federal parts of the federal government aren't always so good. Foundations are sometimes better about it, but background on Stan. So yeah, Stan is a Bayesian model fitting algorithm that so it was developed by Andrew Gellman and team. It's become, I think it's now like a not-for-profit. It's huge. They've got tons of user contributed features. I think it's in R and Python and maybe Stata at this point. It's massive. It uses this Hamiltonian algorithm for more efficient MCMC sampling.
Can I ask a question verbally?
Yes,
Yeah.
go for it, Charlie.
Thank you. I wanted to understand, it seems like these tools are wonderful for helping better understand and assign the true treatment effect. And I wanted to know if I was missing anything from, I don't know if it's philosophical or whatever, to say, is it anything different about what is truly causal versus associative here? I don't know about that. Can you speak a little bit about that?
Yeah. So a lot of these tools get presented, and I probably do this too much too, as if they're magic. Like suddenly now we can do causal inference. It's really no difference. If that response service that the one where I showed where it was all curvy, if that had been linear, and that one variable was the only covariate, we can use linear regression. So this is just fancy linear regression that we're using basically to predict counterfactuals. All of those, the Achilles heel is the ignorability assumption. You have to know that what you're conditioning on in your model, that those variables represent all your confounders. If they don't, you're dead in the water. So that's where the sensitivity analysis piece comes in, because we never really assume that. So people spend, 98% of the research that's happened in causal inference and statistics and other fields has really focused on, how do we do better prediction of those counterfactuals? Maybe not using those words, but in essence, that's what it's focused on. And, that is all fine and well if we've actually measured all the covariates. If we haven't, doesn't actually help us. So what I'm trying to do is kind of fight on two fronts. On the one side, at least let's do the best we can with the data that we have, right? So as opposed to like propensity score solutions to these problems, which are extremely labor intensive and don't get as good predictions, let's make this part easy. And then let's take that time we're getting back and spend it doing better data collection or doing a sensitivity analysis so that we can say how worried we are that maybe we haven't measured all our confounders. And I'm doing work on, I almost included, but I was worried I'd run out of time. I'm doing a whole series of randomized experiments about how people interpret research findings. So depending on how you word it, right? So we teach our students in our statistics classes to use the word association as if you just throw association into interpretation of your regression coefficient, and then you're fine. Then you haven't said anything causal. But then they're using words like increase, decrease, change, gain. Like a change in this is associated with someone. As soon as you hear change, you're thinking causal.
Right.
So, and our experiments bear that out. They also, what's been more depressing about them is that they also show that the thing that's even more predictive of whether people or not assign causal attribution to like a relationship between two variables is the story you tell them about it. Like it's about vaping and anxiety or yoga and falls among the elderly. We've got students as our sample. They have very strong feelings about what they think is causal, even though we're telling them only base it on the information we're giving you.
Yeah.
And so you see huge differences in what they think is causal based on the setting we're talking about, and small differences based on the wording.
The other thing that struck me, I think it's remarkable without really having any functional form assignment that what the tools you're showing handle the nonlinearities that are right there, and I show you where.
Yeah,
I think that's really a strong feature of this.
Yeah,
it's incredible.
I agree. I think we should teach regression by first teaching regression trees, and then the more sophisticated model, because it makes it very clear you're just comparing subgroups.
I think it's a wonderful, it really seems that like, I'm excited to try it out and see so.
Oh, great.
All
And
right,
we've got an educational component that should drop hopefully within a month that's explaining the regression tree stuff.
Nice. Okay.
So.
All right, thank you.
I think of these non-linear flexible models as data hungry. How worried should I be with small samples trying to do some of this? And what's small?
Yeah, it's not that bad. I mean, what helps, it means it's going to rely on the prior more, which is just going to shrink everything towards the grand mean. I would be worried under maybe 50 data points, and certainly you have to change a little bit how you fit you would change the default parameters a little. You don't want 200 trees if you only have 50 observations. So yeah, that would be on the smaller side, but we certainly have we just came out near the top of a data competition where in a set of them, the sample size was about 200 and we had about 20-30 features. So the key is just not overfitting, but it does a good job of guarding against that. So
Great. I must say, I don't know if you've seen Data Robot in action or not, but your interface looked a lot like it right at the start, where you like pick your outcome and throw in your features. And
I have not seen Data Robot. I will look at it.
Well, it's proprietary, and so the fact that I mean, I'm sure there are demonstrations out there, but the fact that you and your team have created something that refined is a testament, because this is an organization with scores of programmers getting all this together, and anyway, it's kind of neat. But I do appreciate I don't want to say idiot proof, because nothing's idiot proof, but the idea that it shows your program shows you what needs to be shown right off the bat is great.
We're working hard on that. Yeah.
Well,
Yeah.
we're butting up against 7 o'clock here. I appreciate your time. I don't see other questions. Nobody's raised their hand, so I just want to thank you again. It was great. Sorry I had to wait so long, but I want to echo Charlie's comment. I'm looking forward to looking at this myself, because as someone who does do analysis in R, it's nice to have automated procedures that you don't have to code yourself. So if there's some good ways to look at it, that really helps.
Great. Thank you. I appreciate the opportunity.
Yeah. All right.
Okay.
Thanks again. Thanks everyone. Hope to see you all March 4th for our next meeting. Good night.
All right.